Thank you. So what the plan today is, so I'm going to resume with the quantum spin Hall effect that we left off yesterday, and then hopefully we'll then discuss 3D topology. We'll use that to get to 3D topological insulators, and then talk about while, which is another 3D topological state. That's as much as I can hope to do. So let me remind you quickly what the picture for quantum spin Hall was. So you remember yesterday we talked about the honeycomb model with next nearest neighbor hopping, and that turned out, and that was the Haldane model, which broke time reversal symmetry and had a Chern number and basically had edge states and quantum Hall conductance, just like the quantum Hall effect for electrons in a magnetic field, but there's no external magnetic field, right? And then what Kane and Millet did was said, well, let's say we want to look at a state which has time reversal symmetry. Not only is there no external magnetic field, but there's time reversal symmetry. And if you have time reversal symmetry, so to make a model which has time reversal symmetry, you take Haldane model for spin up. So, and this was the Hamiltonian here. It's basically the Bernoulli-Hughes-Zhang form. You write a Haldane model for spin up, and you write the time reversed Haldane model, which means complex conjugation and flip the sign of k for spin down. And this is now a time reversal invariant model because you have opposite, your spin up and spin down are related by time reversal symmetry. And so you have two copies of the Haldane model, but because you reverse the time, if you look at the edge states shown here in blue and red for this Corbino disk, then the red spin up moves in one direction, and the blue line spin down moves in the opposite direction. So you have counter-propagating edge modes, right? And then now you might ask, well, this does not seem to have, so this doesn't seem very topological, because if you remember, this will not have any Hall conductance. The Chern number for this will be 0 because you have one component, you pump positive charge, you transfer, you have Hall conductance positive for spin up and Hall conductance negative for spin down. The total Hall conductance is 0. And you don't have this chiral anomaly because not everything is moving in the same direction. They're moving in opposite directions. So is it topological? And one answer was that yes, it is topological because, well, okay. It seems that, okay, at least you don't have charge Hall conductance, but you have spin Hall conductance. But then you ask, is that enough? And the problem with thinking of the spin Hall conductance is that a spin Hall conductance relies on spin being a good quantum number, which it is in this model, but then I can add spin orbit coupling, which breaks spin conservation, but preserves time reversal. And in that case, spin is not a good quantum number anymore, and you don't have a quantized spin Hall conductance. But it is still robust. This was the point that it was still robust because I have a mode, let's say, let me call it plus, which is going in one direction, and I have a time reverse mode, minus, which is going in the other direction. But then the question comes, can I open a gap at this point? Can I get rid of this gapless edge mode? And the answer is no, because if I try to get rid of this gapless edge mode, I would open a gap something like this. But then there's a problem here. There's no Cramer's degeneracy. Right? That pair should have been degenerate, but it's not degenerate. There should have been degenerate according to Cramer's theorem. It's not degenerate, and therefore this is not allowed. Okay? which means this is protected. Okay, so this is where we were mostly till last time. So so questions so far? Okay, all good. Okay, all right. So we know that now. So that tells us that there is a new class of states in 2 dimensions, which are a new topological class, which is if you have time reversals, which is protected as long as you have time reversal symmetry. You don't need spin conservation. And historically, this was quite an important realization because people were trying to talk about the quantized spin Hall effect and then getting all confused about whether spin current even makes sense, whether spin Hall conductance even makes sense, and it shouldn't make sense because spin, if spin is not conserved. Okay, so the next question that we'd want to ask is that we discussed was what is the Laughlin pumping argument, an analog for this? And the statement that we came to, and you can get it from looking at this band structure. So what you do is you plot the band structure of the Corbino of the strip, right? So it's a 2-dimensional strip, and as a function of k. Right? So and k is the wave vector, is the momentum along the Corbino geometry. And what you notice is that, and now remember, when you change flux through the Corbino geometry, it effectively changes k. So when you go from 0 flux quantum to half a flux quantum, then something strange happens. You see that there's only one crossing you get a crossing of the Fermi level, and you get only one or an odd number of such crossings. So now, based on the Laughlin argument, you ask, okay, how many, and by the way, these states that you see here are the edge states, because they're sitting in the middle of the bulk gap. The bulk gap is sort of this guy. So they're sitting in the middle of the bulk gap, so you get an odd number of crossings. Okay, good. And then you ask, okay, so what is the charge transferred between one edge and the other in this case? Yeah. So someone want to try to guess based on this picture? So how many? So this is one edge state, and it crossed the Fermi level once. No, so yeah, that's a good point. You see, at a finite k, you have a flux, and that flux is breaking time reversal symmetry. So you have lost your Kramer's degeneracy. No Kramer's degeneracy. Good point. Okay. So given that, so what is how many charges transfer? Can we just make a random guess? Any guess? Okay, good. I'll take that. And I'm not going to even ask you why. But basically, yeah, these levels are all empty. So, and everything below is filled. So when one level crosses the Fermi level, this is what you saw in all cases before, even with the fermion parity pump. You get one extra electron. So there's one extra electron on one edge, and there's another extra electron on the other edge. But there's something weird about when you get to pi flux. There's a weird thing about one extra electron, and this is that. So that's saying that you have one extra electron on the edge, but then its Kramer's pair is still empty. So you get a Kramer's degeneracy at the edge so if you start with an even number of electrons on each edge, so that there's no Kramer's degeneracy on the edge. If you pump one quantum of flux, now you have an odd number of electrons on each edge. Have a quantum of flux, you have an odd number of electrons on each edge, and you have a Kramer's degeneracy. And this is the topological character of a 2D topological insulator. And why I say this is the topological character is this is the aspect that survives, let's say, interactions. So even if you add interactions to, so I guess you've heard maybe many times, this is the so-called classification of so-called non-interacting insulators, but this is actually not quite true. If you add weak interactions, many of these states survive with the same topological invariant. For example, the quantized Hall conductance, the integer quantum Hall state, even if you add interactions, it still has Laughlin's argument still works. There's nothing in Laughlin's argument that says the system has to be non-interacting. So Laughlin's argument still works, and the Z invariant is fine. Similarly, this fermion parity pump, even though you cannot calculate, even though the mathematical form of the topological invariant, so it would be hard to calculate a many-body Chern number. But on the other hand, the fact that you have a quantized Hall conductance as a fact that survives interactions. And similarly here, the fact that your Kramer's degeneracy of the edge or fermion parity of the edge changes when you have, or actually it's Kramer's degeneracy of the edge changes when you pump half a flux quantum. This is also a statement that survives interactions. No problem. Okay? Yes. Beautiful. Yeah. So that's why I said some of these classes survive, not all of them. So for example, the Majorana chain, which is actually has a sublattice symmetry in one dimension. There's a Z invariant. That one, in the presence of interactions, so in that case, what happens is not every integer is distinct. If integers that are split by 8, they are deformable into one another by considering terms that are interacting. Yes. So that's actually a great point. So yes, so when you add interactions, so I guess what Janendra is saying is that this protection is no longer there. But the catch is that what interaction always does is breaks time reversal at the edge. So what you get is a one-dimensionalizing magnet at the edge when you open the gap. And that breaks time reversal symmetry, and so it sort of breaks this rule. So the issue is that as long as you're in the symmetry class, you can't this thing is stable. But yeah, interactions give you a way of automatically getting out of the class by spontaneously breaking symmetry. Okay. All right. So what I'm going to do next is tell you a way to calculate this 2D topological, because there's a simple answer. So you can ask, when is the quantum, so given a Hamiltonian, so for a BDG I told you that if you calculate the Pfaffian and go between k equals 0 and k equals pi, that'll tell you the bulk topological invariant when there are edge states. And in quantum Hall I told you that you can calculate the bulk Chern number or Hall conductance, and that'll tell you when you have chiral edge states. So the question is, what is the corresponding answer for quantum spin Hall? And the unfortunate, okay, so now here in this case, the direct answer is actually is really messy. It's a Pfaffian is of a complicated object that I don't want to really go into, mostly because it's also rarely used. So if you have inversion symmetry, though, even though it's not needed for the protection of this topological class, having inversion symmetry makes it much easier to calculate the topological invariant. Okay, so what we're going to do is ask, okay, so what's nice about having inversion symmetry? Let me actually make this a little bigger. Okay. So what's weird about okay? So time reversal symmetry gives you Cramer's theorem, but the trouble with time reversal symmetry in a bulk system is that it flips k to minus k. Right? So each h of k itself is not time reversal symmetric because t maps k to minus k. But inversion also maps k to minus k. And it's an inversion, unlike time reversal, is actually a unitary operator that squares to 1. So if you take the product of time reversal and parity, this product, this is sort of a new time reversal. It has a nice property that it preserves k and it squares to minus 1. So you can actually apply this unitary transformation to every h of k. Okay? So question for you guys. So if you have time reversal and inversion, what does it tell you about the spectrum of h of k? Or the eigenvalues of h of k? Okay, I like your second answer. Each of them is doubly degenerate. The E and minus E, I guess, would be, so this P is not a particle hole, it's parity. So nothing takes E to minus E in either of these symmetries. But you're right. T times P is an anti-unitary operator, squares to minus 1. That's all you need for Cramer's theorem, and that gives you that all h of k are doubly degenerate. Okay, good. So that's good. Now let's ask ourselves, if you have when do we get edge states? That's the thing that let's ask ourselves. When do we get edge states? So I imagine, I have some y direction and some x direction, and I have, let's say, I have some term in the Hamiltonian, with some mass term in the Hamiltonian, which changes. Okay, so what do I? Let me see. So what do I mean specifically? So let's say, so I guess what I'm trying to do is find out a condition for when I have helical edge states. All right. So in that case, I have. So remember each. So my inversion and time reversal are still good symmetries. So which means every eigenvalue is twofold degenerate. So I have a label sigma that labels this twofold degenerate eigenvalue. And I have an index B, which represents whether it is a left mover or a right mover. And so I have linear dispersion at the domain wall. Right? So I'm kind of working my way backwards and trying to ask, when can I get this helical edge mode in the bulk? What's the condition? And then on the other hand, what I have is and then I have a mass term which wants to gap this helical edge mode as I move into the bulk. So which means that, so this, again, it's not breaking this inversion times time reversal. So what I have is that I have some m of x, which is flipping left movers to right movers. So far so good. So I have some term like this, and m of x is position. Yeah. All right. is so I have ky. So ky is a good quantum number. So I'm looking along the along this direction, and then basically I can use. So I have this Hamiltonian, right? So kx. So I have kx is ky is a good quantum number and is fixed, and then what I'm doing is I have this and I basically now I have a momentum and an m of x. So this should remind you of the one-dimensional Dirac equation that we solved before for the Majorana case. Remember what I told you, the typical way of getting a topological zero mode near a phase transition is to start with being near the phase transition, which is what I'm doing here. So I have this linear modes along kx, and then I open a gap, which is m of x, and then whenever m of x changes sign, this was the index theorem, I get a zero mode at the boundary. Okay? So I would get a zero, I would get a zero energy mode at the boundary, so which means that So if I'm looking at ky equals 0, so that ky goes to minus ky, it's what's called a time it's a time reversal invariant momentum. It's momenta which go to themselves under time reversal. If I look at that one, so that the symmetry constraints are obeyed, and along at this ky, when m of x changes sign in the x direction, then I expect to see a zero energy mode, provided m of x changes sign in that direction. That's the condition, right? So this is just to remind you, ky is fixed. Ky along this direction is fixed. Momentum along y direction is fixed at 0, and I'm looking at a domain wall along the x direction. So far, so good? Okay. So anyway, again, whether this argument is a little, I have to admit it's a little involved, but it's the final conclusion that I guess is key, that you get a zero mode, and then you ask yourself, okay, I have a zero mode at ky equals 0, zero energy mode. Now, how do I derive that it's linearly dispersing? So for that, as a matter of principle, I have to go away from ky equals, so I do something, and this is also a generic trick. So I have zero modes, and then on top of that, I add something called k dot p perturbation theory. So what that means is I can write h of ky at small ky as h at ky equals 0 plus ky times a velocity operator. And the velocity is just this velocity is just the derivative. So this is just a Taylor expansion. I can do a Taylor expansion to lowest order, and I get this expression. And then if I have two eigenvalues, let me call them left and right, which are degenerate at e equals 0, then I can take matrix elements. So how, am I going too far? Excuse me. Am I going too far to the right, or it's okay? All right. Then I can diagonalize the velocity operator, and I get these two linearly dispersing modes. So that's how I get the spectrum if m of x changes sign. Yeah? Okay. So now the next question is, okay, what is this weird condition that m of x changes sign? That's the next question to ask. So what is this weird condition that m of x changes sign? Right? So remember, let me draw the band structure along x again. Something like this. So this is E as a function of kx, but ky is equal to 0. All right? And this point is kx equals ky equals 0. And these are what are called time, this is a terminology you'll find a lot. They're called time reversal invariant momenta. They're the points which are special because at these points, not only I have twofold degeneracy, so not only do I have eigenvalues of the combination of time reversal and parity, but I have them individually. Okay, so everything is twofold degenerate here. And if you remember in the notation I have over there, this is sigma. But one of these branches I labeled plus, and this branch I labeled minus in this formulation, because this was the one that was moving to the left or to the right. Yeah, this was our label. Now I ask, what does parity do? So these are eigenstates of time reversal times parity. Now I ask, what does parity do? Parity takes me from plus to minus and vice versa, right? Because it has to flip k to minus k. So that means that the combination, so the eigenstates of parity are linear combinations of plus and minus. So this perturbation that I had, m of x times plus sigma minus sigma plus Hermitian conjugate, this I can rewrite as m of x times e sigma. So if I diagonalize and go to the symmetric and antisymmetric basis, then I get so what it tells me is that m of x is the splitting between this state, these even and odd states, parity states. So even though parity was not a good quantum number away from k equals 0, ky equals 0, or kx equals 0, parity is a good quantum number on the line kx equals 0. And whenever I have a mass change here, so I already told you based there that when I have a mass change there, then I have a 0 mode. So what happens when I have a mass change here? Right? Then it basically I go from, so the mass change looks like going from a situation where I have even at higher energy, odd at lower energy, to odd at higher energy, even at lower energy. Right? So when mass changes sign, the even one goes down, the odd one goes up. So the final conclusion, let me see, I should have it written out emphatically somewhere, is this. That so when you have inversion symmetry for a Z2 topology, for the quantum spin Hall system, all you need to ask yourself is how many even parity states. So you need to count how many odd parity states are occupied. Right? So that's the ultimate conclusion. So let me make this. Yes. 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 Sorry. Yeah, I know. And this is an unfortunate mixture of. So let me just since you asked that, let me just double clarify. So the strategy here is I'm looking at a domain wall, right? But I'm looking at it near, and I'm using my strategy from before, which is that I'm looking near the phase transition of the bulk. Right? I'm looking near the phase transition at the bulk, and near the phase transition of the bulk at ky equals, so, and I'm looking at a domain wall which is parallel to the y direction, which means ky is a good quantum number. But I want to take advantage of my inversion. So I am choosing ky to be 0, which is invariant under this inversion. And then I'm looking at the dispersion along kx as a function of kx near the transition, which is this avoided Dirac kind of thing. And I have a mass, which is this gap. And my domain wall is where that mass changes as a function of x. These are all bulk states so far, right? And then the statement I make is that I use the index theorem to argue that when mx changes sign, then basically based on my index theorem from before, I must have a 0 mode at the domain wall. And now that's the surface state, the 0 energy mode. And then I can use the velocity operator to calculate how it disperses. And one has to go one way and the other has to go the other. That's the argument. Any other questions about that argument? Yes, it's a domain wall is an interface between the two mass signs, and one of those is topologically trivial, and the other one is topologically not trivial. One mass sign is topologically trivial, and the other is not trivial. Right? And now, in this part, what I'm arguing is that what I'm arguing here is that the mass has to do with the parity eigenvalue of which orbitals are occupied and which orbitals are not occupied. So this mass, which seemed kind of abstract here, ultimately is the parity eigenvalue. Right? So at the transition, at the domain wall, what happens is one odd parity orbital and one even parity orbital flip sign. Right? So let me write down the final recipe, which is simple. Final recipe is look at or focus on trim, which are time reversal invariant momenta. These are the momenta where k is equal to minus k. And at these momenta, the topological invariant is equal to the total parity of occupied states. Right, so this seems a little abstract, so let me just tell you, for those of you who are familiar with semiconductors a little bit. So the reason that it's rather easy to come up with topological insulators is because with this recipe, if you go back to your basic atomic physics, s orbitals, so what are the parity of s orbitals? Right? Even, right? Okay. And what's the simplest orbital you would think of with odd parity? P. Beautiful. So most semiconductors basically are made of s and p orbitals, right? Most of your carbon, silicon, germanium, tin, lead, all those guys, they're just s and p orbitals. So all you have to make sure is, and actually, for those of you who remember a little bit of basic semiconductor physics, in the band structure of most semiconductors, the highest occupied state, that's the top of the valence band, is made of p orbitals. And the lowest conduction band is often s orbit. And then when you add spin orbit coupling, and okay, why spin orbit is important for this, I guess, is I don't really have a great intuition for, but typically this is well known for all semiconductors. This s-like state tends to come down, this p-like state tends to go up. So, and when you get a crossing between these two, then you can get a topological insulator, or you will get a topological insulator. Okay, provided, okay, it happens at an odd number of these time reversal invariant momenta. Usually this just happens at k equals 0, and you don't have to worry about the other k's. Okay? Yes? Yes. Oh, why is that? No, I'm saying if it is so. I didn't say, I'm not giving you the condition for when it's the topological. I'm giving you the condition for when it is a topological insulator. I'm not really telling you how to make a topological insulator. But I'm telling you that if you can somehow change your Hamiltonian so that you flip the energies of the odd and even parity states. And this is now a microscopic question of what you change in the Hamiltonian to make this happen. Then you'll have a topological. Exactly. So actually, this leads me to a great question. So I guess you might worry that when I say S and P orbitals, this is isolated atoms, and not a crystal. So you might worry that, oh, now what about when I have a crystal? I have block states. But you see, the thing about at k equals 0, parity is still a good quantum number for the Hamiltonian. So you take your Hamiltonian, you diagonalize it at k equals 0, and apply the parity operator and see what is the eigenvalue. That's the recipe. And if the even one is below and the odd one is top, most likely you have a topology. Yeah, so just to zoom back, what inversion made easy was it helped. So I needed inversion because ultimately I have so I wanted to use a double degeneracy at each k point. I wanted to make the bulk Hamiltonian doubly degenerate at each k point, and that makes it because I wanted to effectively get rid of a spin degree of freedom and make my system more manageable. No, time reversal just tells you that E at k is degenerate with E at minus k, right? It doesn't tell you that it's doubly degenerate at the same point, right? So if I broke inversion here, for example, this band structure would look like something like this. So you would have Cramer's degeneracy at k equals 0. This is called a Rashba type spin orbit splitting. You would have degeneracy at k equals 0, but at other k's it's split. Right? But that makes my life too complicated, yeah. So if you remember when I solved my index, so when I solved this problem, I reduced it to an index theorem. I'm talking about the derivation. I reduced it to an index theorem. I had this index sigma, and I didn't have to worry about it at all. Right? It was just diagonal. From a practical point of view, this parity is only defined if I have inversion symmetry k equals 0. So the form of this topological invariant only makes sense if you have inversion symmetry. If you don't have inversion symmetry, one can still calculate the invariant, but it's a much more complicated calculation. Okay, any more questions about this point? So this was the beautiful realization of Foucault and Millet, that if you have inversion symmetry, you have this nice compact form for the topological invariant that depends on the band structure of only the time reversal invariant points. You don't need the whole band structure. You just need to make sure that you get band inversion. And a funny historical note, actually, this story, all the ingredients here, other than the topological protection, this is standard K dot P perturbation theory for semiconductors from the 60s, the so-called Luttinger Hamiltonian. For those of you who've heard it, it's not even Luttinger liquid. It's just standard semiconductor Luttinger Hamiltonian. So at some level, it is surprising that it had to wait till 2005, starting from 1950, for this stuff to be discovered. This is just band structure. And as you would guess, this actually didn't wait till 2005. The calculation that if you took a Luttinger model with even and odd and went through a mass sign change, which is of course motivated by the index theorem, But in the semiconductor case, this was done in the mid-'80s, mostly in the Soviet bloc. And then, but somehow, because this topology, the word topology didn't get stuck to it, this Kramer's thing was not really realized. People didn't care very much. And I guess experiments weren't exactly good enough to see this. So basically this was theoretically observed and then dropped. And then happily forgotten and in some sense rediscovered in 2005. And so this was, and I would not have known this other than talking to like Viktor Yakovenko, my Russian colleague. He's the one who remembered 80s Russian work. Anyway, okay. So yes. Oh, thanks. So actually here, this is a much simpler version of K dot P theory than the Luttinger I'm talking about. So here, all I'm saying is, so what I told you from the index theorem is that I got a zero energy mode at ky equals 0. But I did not tell you that I have velocity edge modes that are going in opposite directions from that. I just know the crossing point is that there's a crossing point at 0. That's all I know. So to understand what happens after that, to calculate that, I would take my Hamiltonian around ky equals 0 and expand it in a Taylor series to first order, let's say, if I want the lowest point there. And the first order is a derivative of the Hamiltonian, which is the velocity. So then if I diagonalize my Hamiltonian in this basis, then I diagonalize this perturbation in the basis of the degenerate states, then symmetry tells me, okay, I can do the calculation, but symmetry tells me that one of the velocities has to be positive, the other velocity is just by time reversal. Symmetry. Right? They can't both be positive because that would violate time reversal. Right? So that's basically it. Okay. Yeah, there's nothing really that ensures that V is finite. So you could have fine-tuned places where V is 0. And actually, that's actually an interesting, that reminds me of an interesting thing about, let's say, even fractional, just quantum Hall edge states. If you look through Xiaogan Wen's papers and about the derivation of this is the alternative view of the fractional quantum Hall, I guess, then I don't know if Jen Indra is going to get to it, but you have a Luttinger liquid description for the edge states for all these one-dimensional systems. And Xiaogan Wen derives it from Chern-Simons theory, and the funny thing is that the default answer he gets for the velocity is 0, and he has to make a weird choice, or he has to boost to get something that is not 0. But in any solid-state system, 0 is a fine-tuned point, so it's not likely to be 0. Okay. So that finishes the story for the quantum spin Hall. The bottom line is that there's a topologically protected state in 2 dimensions, which is protected by time reversal and which has these so-called helical edge modes, right? And you can calculate when that happens from parity. Okay, I'm skipping about talking about experimental materials for lack of time. So the next story is 3 dimensions. And I have to say that this is, so the history here is also kind of interesting. Here's my Brillouin zone in 3D. So the history here is kind of interesting. So 2005, Kane and Millet wrote their paper about the two-dimensional system. And that was kind of interesting, but then actually I was a grad student at Berkeley and we were all excited, but down my office, 2 doors down, Joel Moore was actually asking the real sort of deeper question or more interesting question. So me and Ashwin, we were just trying to understand like what happened to the quantized spin Hall effect, which is some detailed thing. And the question that Joel asked, and turns out that Rahul Roy and Fu, Kane, and Millet about within a week somehow magically asked the same question, is that like, what can we generalize this to 3 dimensions? And the reason this was very exciting at that point was that there was no known topological state in 3 dimensions. We had quantum spin Hall was nice as a topological state, but it sort of looked like quantum Hall, which was also in 2 dimensions. It was in fact a wimpy version of quantum Hall because it was not even protected against time reversal, like breaking time reversal. So it was a weaker version of quantum Hall. But then, so Moore and Balance and Rahul Roy and Foucault and Millay, they all wrote papers on this within a week. And I guess I can't resist. So Rahul Roy's story was sort of the most interesting among this. He was a solitary grad student in Urbana at that point, and he just posted a paper on the archive describing this. But being a grad student, his paper writing skills were not exactly were not perfect. So it took 3 years for referees to make sense of what he was saying. And so everybody else's paper got published, but his paper had to wait. And Charlie Kane was the one who sort of like told like guys like, hey, look, this is correct. He's got it right. So that's a good question. I do not remember off the top. No, absolutely no. He was certainly not the last. I do not remember for sure if he was the first. But this is easy to check. I did not. But this was quite interesting. Okay, but so the basic idea, when all the dust has settled, the basic idea is of going from 2D to 3D is not that complicated. The basic idea is so again, you're going to do the same thing that we did with quantum spin Hall. In quantum spin Hall, what we did was we said, let's look at the domain, the interface, surface, and see when can we get a helical edge state. So in this case, let's ask, I have a 3-dimensional crystal, when can I get something interesting on the surface? And the nice thing about the surface is that 2 of my momenta are good quantum numbers, right? I only have one direction where I've lost translational invariance. So I can look pretty much at the full, so let's say I'm looking at a surface which is perpendicular to the z direction. Kx and ky are still good quantum numbers. So if I take a ky equals 0 slice of my Brillouin zone, right? I set ky to 0, and I look at the band structure here. What do you think could happen? What do you think could be interesting about the band structure for this KZ-KX plane? Anyone? So it's the KZ-KX plane so the system still has the same symmetries as the quantum spin Hall system. So it has time reversal, which is what we needed. So so what does that suggest? What could happen with this? If I just looked at the Hamiltonian as a function of kz and kx, and based on what we just talked about, what could be interesting? Sorry? The Hamiltonian could become gapless over there, but let's say it is gapped. And based on what we just talked about in 2 dimensions, that is true. But this plane, this 2D Hamiltonian, okay, so in the interest of time, let me give away the answer. It's a 2-dimensional Hamiltonian. So this is a Hamiltonian which was a function of 3 things, kx, ky, and kz. If I set ky to 0, it's a function of kx and kz. It's a 2-dimensional Hamiltonian. It has time reversal symmetry, so it could be a quantum spin Hall system. Right? This plane could be a quantum spin Hall system. That's basically the simplest possibility that could happen. Right? Does that make sense? Because again, it has the same dimensions as the quantum spin Hall system. It lives in 2 dimensions. Right? So for example, if I calculated the Fermi, let's say I have inversion symmetry and time reversal as I did before. If I have the total parity of occupied states. So as was mentioned, parity is a good quantum number at each of these time reversal invariant points. Just as before, this statement did not depend on dimension. So if I think about these 4 time reversal invariant points and calculate the total topological invariant, this can be topologically non-trivial. Right? Does that make sense? No. No Chern number, because I have time reversal. I have preserved time reversal invariant. So Chern number for each plane is 0. Right? So I have to think about in the symmetry class that I am in now, which has time reversal. And so what I have, so the time reversal, the topological invariant Q is this total parity of each of these time reversal invariant points. How many odd orbitals are there, right? And I'll calculate the total topological invariant, this invariant here, Q, on this plane. And that can tell me whether this is this plane is topologically non-trivial. Right? So far, so good. Okay. So are there any questions so far? So this is the key idea that I want you to get. So this is basically the key idea for 3-dimensional topological insulators. The rest are sort of consequences. Yes. Yes. That's a great point. It is not a 2-dimensional. It is. So that's okay. That's a great point. It's not actually. It doesn't actually live in 2 dimensions. It's sort of a fictitious Hamiltonian. This is actually a key trick in the field of topological insulator called dimensional reduction. But it still is useful. That's why I made the statement that if you're looking at a surface perpendicular to the z direction, ky is a good quantum number, right? So it is telling me something about the surface band structure. And what it's telling me about the surface band structure actually very specifically, if this is if this plane kx kz is trivial, right? I can plot the surface band structure at ky equals 0. Ky equals 0 as a function of kx, which is still a good quantum number, and I expect quantum spin Hall edges. Right? And I expect quantum spin Hall edges as long as I think the product of the fermion parity at 0 and pi, these 2 fermion parities, as long as that product is, not fermion parity, orbital parity, as long as the product of these 2 orbital parities is odd, then I expect this at kx equals 0. Based on this argument so far, right? So now here comes the interesting consequence of 3 dimensions. Let me now look at this plane. So I set kx to be 0 and look at the kz-ky plane, right? For the same dispersion. Then if I have inversion symmetry, inversion symmetry, again, this and this product is still, this total orbital parity is still negative. And so I can just rotate my structure by 90 degrees and I get a similar answer. I get that E at kx equals 0, ky, this is, again, looks like that. Right? I apply the 2-dimensional argument to the xz plane and the yz plane. So far, so good. Assuming that, again, that this at x equals y equals 0, this is non-trivial, this line. Is that good? So far, so good? Okay. So now, given these two, now the next question is, so again, these are the surface, this is at the surface, which is the domain wall. Now the next question is, what do you think happens when I come, so at ky equals 0, I get a pair of lines. At kx equals 0 as a function of ky, I get a pair of lines. What do you think the dispersion looks like as a function of kx and ky both? These are just two sections of what it looks like with kx and ky. So what do you think it looks like as a function of kx and ky both? Sorry? So cone is the right word, but it's not double. So if so basically I just get a cone, a Dirac cone. So let me just try to draw a picture here. So my claim is that energy as a function of kx and ky looks like a Dirac cone, a single Dirac cone. Right? And just think about it. If I take this Dirac cone and I slice it at ky equals 0, so it's this section, what am I going to see? I'm going to see two lines. And if I slice it along the x direction, if I slice it along any vertical section, I'm going to just see something like two lines like that. Right? So ultimately the conclusion is that if the product of this parity is odd with inversion symmetry, then I should have a Dirac cone at kx equals ky equals 0. Yes. Yeah, absolutely. I have it. It could be arbitrarily anisotropic, I guess, as long as it doesn't touch. But yeah. But at this point, yeah. But I do know just from the 2D topological insulator argument, just by stacking together topological insulators in momentum space, I can obtain that in 3 dimensions. It tells me, so basically this is the magic of dimensional reduction. By using momentum space to go from one dimension to another, I can make a statement about a higher dimensional band structure from understanding a lower dimensional band structure from quantum spin Hall. Right? Yeah, that's a good point. So if you have, so there are some constraints on how that can be. So the only way that can be, for example, it can't be if this pair of, at least with inversion symmetry, it cannot be, that can't happen if this pair looks like, if this pair is odd in total and odd in parity, because if this is, okay, it can happen if this is odd and that one that at the back, that dashed line is also odd. And then this can happen, but then you would have actually two Dirac cones, one at kx ky equals 0, and the other at the next at that point. So when you have, so you can have an even number of Dirac cones. When what you're saying, when that happens, you have an even number of Dirac cones, and that's what's called a weak topological insulator. And the reason it's called a weak topological insulator is, okay, so the next argument I was going to make is that this Dirac cone is actually stable to disorder. It's a single Dirac cone. If you can, so here I use translational invariance, I use momentum as a good quantum number, but now I can ask what happens if I disorder it, and I can argue similar to the quantum spin Hall, this Kramer's pair. I also have a Kramer's pair here, and I can't get rid of that Kramer's pair. But if I have two Dirac cones, I can actually use disorder to mix them and get rid of it. So that's the question. Yeah, yes. Yeah, good. Yeah. So that's right. So the only thing I cannot get rid of is that there is a surface state which is not localized completely, which conducts. Okay. Yes. Yes. Quantum spin Hall. No, so the argument that I said that you can have quantum spin Hall in some phases and not on the other, that holds even with inversion symmetry. So I'm just saying, so remember I had, where do you go? So I had this Brillouin zone, right? And the way I was calculating the invariant is I take the orbital parity of each node, each of these trims. And I take it to look at a plane, I just take the product over that plane. And then on the other plane, I take the product over another plane, and so on and so forth. Right? So this is all with inversion symmetry. Now, if you break inversion symmetry, the argument I can use time reversal to say that the Dirac cone, once you get a Dirac cone, it's going to still be stable. But beyond that, I can't. But again, it becomes hard to calculate the invariant. But actually, it still remains true that if you calculate the invariants of planes, you can still get the 3D topological invariant. This is still true. Okay. Yeah, I mean, unfortunately, I think I have this kind of inflation kind of thing going on, so I'm going faster and faster. So the last topic that I want to talk about, and I have half hour for, is while. So, but again, okay. So I guess I got some questions about topological insulators, so I'll keep going. Okay. So now, all right. Whoa, that's really big. Actually, I'm not going to use this very much for a while. Let me see if I have a nice picture. Okay. So, while points. So actually, the 3D topological insulators is a good way to jump into these so-called while points or while systems. So the basic, okay. So the 3D again. So the two features of the 3D topological insulator that we will take over is we have a 3D Hamiltonian, right? It's a bulk Hamiltonian, and in the 3D topological insulator case, if you fixed certain momenta, if you're looking at the surface, then you can think of the resulting two-dimensional Hamiltonian as a topological class, as a quantum spin Hall system, right? Now, from your questions, many of you mixed up quantum spin Hall and quantum Hall, so I'm sure one natural question you would ask is, what if instead of having the two-dimensional section be quantum spin Hall, what if it were quantum Hall? What if it were a Chern insulator, right? That's the natural question that you can ask next. And the answer actually is going to turn out that the answer is a while point. Okay, so that's you get a while system. So let me give you that picture first. Okay, so again, I have a I have some three-dimensional system. And let's say this is some physical surface. Okay. And this is Z, but X and Y are still good quantum numbers. All right? So X and Y have translational invariance, so Kx and Ky are good quantum numbers. All right? So next what I'm going to do is I'll fix, let's say, one of the Ks and look at the Hamiltonian. So let me draw it here. So what I'm going to look at is this X Z plane with, let's say, Ky equals Ky not fixed. Okay? So I'm just looking at the surface. I'm interested in understanding if there's anything interesting on the surface. And so from there, I have a two-dimensional Hamiltonian which depends on X and Z with Ky 0 fixed. Right? And in principle, this could be a Chern Hamiltonian, let's say a Haldane model. Right, so I could imagine I somehow stacked Haldane models in the y direction so that I have a Hamiltonian which at some K0, Ky0 has a Chern. So I went over that briefly yesterday, but just briefly. So it's a honeycomb model with next nearest neighbor hopping, and the interesting thing is that its band structure has a Chern number, which means it has Hall conductance. So it's like a quantum Hall system, but it's a lattice model with no external magnetic field. Right? And you get it very straightforwardly by taking honeycomb model with next nearest neighbor. That's what Haldane discovered. Okay, great. So the question to you guys is, what does that tell you about something about the surface state? Let's say I had a quantum Chern number of 1 for this. What does it tell you a little bit? What does it say that it's some surface state or something like that? Sorry? It should have. Okay, and so yes, so it should have surface states, and basically, why? Because this, again, on the surface, Ky is a good quantum number, so if I fix it to some value, this Hamiltonian will have these Laughlin, these edge states, these Laughlin edge states, right? So because this is a quantum Hall Hamiltonian, there are some edge states. So whatever you have on the surface, so I don't know what I exactly have on the surface, it should be a function of Kx and Ky. But this should have the same dispersion, at least at Ky0, it should have the same dispersion as the edge states, the chiral edge states. So it should be V times Kx. So I have something, at Ky equals 0, I would have something that is V times Kx. Okay? So this is okay. But now what I'm going to argue, okay, so this suggests that it's kind of like a 3D topological insulator. But there's going to be a surprise. If I make Ky0 go to infinity, right? If I make one of the momenta go to infinity, at that point, I should literally empty out the band structure. I'm going to very high momenta. I should, at least intuitively, I should have no electrons at very high momenta, which means that my Chern number, so for this, the Chern number for this h x z ky 0, this should be equal to 0. Right? So at very high momenta, positive or negative, I have no electrons that are occupied, and occupied electrons are what allows me to have edge states. So I should really just have zero Chern number. Right? So now I have a weird situation. I'm demanding that at some ky0 I have a non-zero. So if I look at Chern number as a function of ky, at some ky0, this Chern number is 1. But at very large, let me say beyond some momentum, ky0, it should be 0. And on the other side, it should be 0 as well. So ky goes to infinity or minus infinity. It should go to 0, and it should have some. So I'm imagining that it has some value, non-zero value in the middle, but it has 0 beyond some point, right? The fact that it is non-zero somewhere, that's an assumption. I'm imagining I cooked up a Hamiltonian which does that. But the fact that it has to be 0 eventually, this is sort of a requirement. So the question to you is, again, now, based on what we have learned so far, do we know anything about this Hamiltonian at that critical point? At this point where the Chern number changes? Sorry? Beautiful. The bulk gap should close, right? Because I have, as a function of ky, I have a topological invariant that is changing and then certainly goes from 0 to 1, so this should be gapless. So this is the key difference between the 3D topological. So if I tried to stack quantum spin Hall and get a topological system, I got something that was, and okay, you can go back and think about it. Well, because in that case, ky0 had to be at only like 0 and pi, some discrete values, we didn't run into this issue that we could make it gapped. But if we start with quantum Hall, no symmetry is required, and I have to have gapless points. So the system that I get by stacking quantum Hall has to be gapless. And this, so now let me ask, what does this gapless point look like? So I've told you before that, so h, I'm looking at the function of kx, kz, and ky0. Near the transition, I said that it had to look like a massive Dirac theory. Because at the transition, you have a gapless point. Near the transition, it has to be something like Vx, Kx, sigma x, plus, let me say, Vz, Kz, sigma z, plus some mass which depends on ky0 times sigma y. All right? And this mass is what changes sign at the transition. So near the critical point, this one is linear in ky, and so this becomes Vx, Kx, sigma x, ky, sigma y, plus plus Vz, Kz, sigma z. So I just took this mass and linearized it in ky. Right? And this is exactly what high energy people have called a Weil Hamiltonian. All right? So Basically, it's a three-dimensional generalization of graphene. Graphene had a two-dimensional, or the surface state of a 3D topological insulator. This was a two-dimensional Dirac point. We used to still call it a Dirac point. This one looks like a Dirac point, except that there's also a third momentum and a third Pauli matrix. Okay. Now, why is this so interesting? So if you look based on this argument that we did by deriving it from Chern insulators, we know that this thing has to be topological. This transition, this argument that I had a Chern number and I go to Chern 1 and I go to Chern number 0 and I have a gapless point, this gapless point is not going to go away by just like adding a perturbation. So usually with the surface state of a 3D topological insulator, you apply a magnetic field, you open up a gap. But this is not protected by any symmetry. So this should stay. And the beautiful thing about this while Hamiltonian is that you can see right off why it stays, right? Because let me get rid of the anisotropy of the velocity. That's just a rescaling. If I have my Hamiltonian to be V sigma dot K, right? I assume all the V's are the same. If I add any perturbation to it, B dot sigma, right? So this is a 2 by 2 Hamiltonian, so the simple perturbation that I could add is I could just add a random magnetic field. This one I can just redefine as a shift in K. So V K plus sigma dot V over V. So while point is still there, any perturbation just moves it around a little bit in momentum space. So it's still completely robust. Okay? So far so good? Okay. So now let me just come back to this. So the gap is bulk is gapped. And now I come back to asking, what about the surface? All right? Rajdeep? No, it is still a good quantum number. I mean, so you don't have translational invariance in KY, but you have translational invariance in Y. Right? So KY is a good one. Okay. So the next story is, okay, now what about the surface states? So I said they're this chiral edge states. That's what they roughly are. But now that we know the KY structure, we can ask, what do they look like on the surface? And the answer is that, so basically what should happen is that I should have this, I have to imagine something where the dispersion looks like this, up to some KY. So this is a function of KY. And then it disappears. So if I look on the surface, so now I want to plot energy. And now this is a question of making a three-dimensional plot, which is always non-trivial. And I'm just trying to see which direction is the easiest to visualize. So yeah, so I'm going to choose this to be my x-axis and this to be my y-axis. All right? So for some range of ky, let's say from here to there, I have some linear modes that disperse like that. So I have a plane. So I have a plane that goes up like that. And then beyond this value of ky, it's gone, right? And so if you think about the energy equals 0 surface, and I'll use another color here. the energy equals constant. So the energy constant surface is funny. It's a line. It's a line that just ends at 2 points. Right? If I look at the surface dispersion and I look at what we call the Fermi surface at energy 0, which is a constant energy line, it's a line that ends at 2 points. And but actually this dispersion continues below. That's fine. But so this thing is the famous so-called Fermi arc. And the terminology was not invented with Weil. This is a history. It started in the high TC cuprates. When he did ARPES, angle resolved photoemission, it looked like the Fermi surface of the cuprates in certain phases had the zero energy line. It just started and it ended at a point. It just started at a point and went as a line and then just ended in free space. And you might ask, okay, that looks weird. You've never seen a Fermi surface which just ends at some point. But actually, it's worse than that. And this was investigated by Ashwin in a few years ago. Well, Ashwin, I think he was the one who started. He was the first person to realize that these things can happen in solid state. And then a few years later, he realized that, okay, what is really weird about this, these kinds of Fermi arcs? And what is weird is you can ask, what's the magneto oscillations, or what's the magnetoconductance? Like what do the Shubnikov-de Haas oscillations look like, right? So Shubnik, just to remind you, Shubnikov-de Haas or de Haas van Alphen is basically the way you verify that there is a Fermi surface by applying a magnetic field, and the electrons go around in cyclotron orbits, and with the Landau level kind of spacing, and that gives you oscillations in conductance. The trouble is, in a cyclotron orbit, the energy of the electron, because it's in a magnetic field, it can't change. Magnetic field can't change energy, it can only change momentum. So the electron actually always makes a loop in Fermi surface space. You can ask the question, when you have a Fermi arc, where do you make the loop? Right? Because the Fermi surface doesn't even go in a loop. It starts at a point and ends at a point. So the answer turns out that at this point, at the ends, you have gapless modes. So in some sense, the orbits go into the gapless modes in the bulk. So you get quantum oscillations from orbits which start at one end and then go into the bulk at the other end, and then go to the other surface and then sort of come back up. So this is a weird thing. So but talking about a magnetic field gives me an opportunity to talk about the chiral anomaly for Weil Hamiltonians. So this is the sort of and again, these are all borrowed from high energy physics, but it has beautiful solid state interpretations. So the question that one needs to ask is, let's say I take this Weil Hamiltonian and I apply, and I set one of the momenta to 0 for a second. So I apply a magnetic field along the z direction so that I set the z momentum to 0. So this is now kx, ky, e, and z has been set to 0. Okay? And then I ask myself, okay, I apply a magnetic field, so what are the Landau levels? So what it turns out is that because of the Berry phase, there is a 0 energy Landau level, and then there are other ones. So there's a Landau level at exactly 0 energy if you solve this. And this is an exercise that you can do following basically the same calculation that Janendra did, but it turns out that if you just you use minimal substitution here, it's similar. You get a harmonic oscillator again, but this time the harmonic oscillator gives you a zero energy state. Right? You get rid of the half from the harmonic oscillator because of a Berry phase. So you have a state like that. Now but turns out that this fella is an eigenstate of sigma z. And you know that this makes sense because if I set kz equals 0, this Hamiltonian anti-commutes with sigma z. So the zero energy state is going to be an eigenstate of sigma z, if it's non-degenerate. So what that means is that if I now plot this, again, same trick that I did with topological insulators. I take my zero energy Landau level, and I ask what happens when I do K dot P perturbation theory with sigma z. So as a function of sigma z, this mode just disperses linearly. Bz kz. So at kx equals ky equal, well, the zero, no, I shouldn't say that. It's the zeroth Landau level. The zeroth Landau level is chiral. Right? It just goes in one direction, in the positive z direction. And as with quantum Hall, we learned, okay, so this, when in the context of quantum Hall, as we discussed yesterday, this is actually anomalous, right? If you have a mode that is going in one direction, now you have a weird thing that if I apply an electric field, then charge is going to get pumped out. You're going to get a charge that just gets generated. And it turns out that this is related to the anomaly with the second Chern number. Again, those are just words that I don't want to go to, but if you look at, I guess the easiest place to, there's a dimensional reduction paper by Zhang, by Shucheng Zhang, from a while back, actually. And what he says is that you're going to get something that is some constant times E times B. Right? And you can see that you needed the B to get the Landau levels, and then you get a current density from the fact that your electrons are just driving up particles and momenta in that direction. Okay, so you're just generating. So the weird thing about a while is that if you apply a magnetic field and apply an electric field, you just get charge coming out of space. Of course, that is anomalous, can't happen. Charge is conserved. But thankfully, if you remember, there were two gapless Weil points with so-called opposite monopoles. So you lose charge from one and you gain charge in the other. And that chiral Landau level also explains the anomaly with the Fermi arc. So let me just draw the other Fermi arc and complete this picture, and that'll be the end of the story. So on the other surface, there is another Fermi arc. And this chiral Landau level is what connects these two guys when you have a magnetic field. So you go up one, you come down the other. So, and this thing, I think, Haldane has called Fermi surface plumbing. Okay, so, all right. So if I think that's as much as I have really time to talk about. So yeah, if you have, so I'll just take questions. Oh, plumbing. Yes, plumbing. It's like a pipe for your Fermi surface electrons. Okay, so yeah, so I think that's yeah. So that, and this is really the rage that people. This is so all the other things that I talked about, Majoranas, topological insulators, they're sort of fallen behind in the condensed matter fad world, and Weil is the new fad right now, at least. So anyway, so that brings us to the present. So I think that's that's it. Right. So yeah, this was rather fast, but so you can ask anything that pops in your mind. Yeah. So if you think about quantum Hall, right? So you get a Chern. So the Chern number depended. So you had Landau levels. You had you had the first Landau level, the second Landau level, and so on and so forth. You got one chiral edge state when your chemical potential was above the first Landau level but below the second Landau level, right? So you needed you needed a set of electrons at first Landau level to basically be occupied. Now, if you imagine that you take your Hamiltonian and you add a ky squared dispersion to it. So as ky goes to infinity, the energy of all these states is going to rise. And your first Landau level is going to basically become at very high energy. So at large ky, you'll basically be below the first Landau level. Right? So then there will be no electrons to form your quantum Hall state. You cannot have edge states. Basically, at large ky, you shouldn't have. Yeah, no, that's a good point. So, I mean, in most reasonable physical systems, you would have a dispersion along ky. So the good point is that actually in a crystal, this is slightly oversimplified argument, but actually you can make an argument that the total Chern number of your Hamiltonian, that has to really be 0. But I wanted to avoid that technical. But for many systems, this makes sense that you're going to have some dispersion as a function of ky and Chern numbers. Yeah. So remember the rules for a cyclotron orbit in momentum space. So you should really think in momentum space because the magnetic field doesn't really break translation. So it's really in momentum space. And in momentum space, but energy is going to be conserved. So it has to be an isoenergetic surface, right? So the isoenergetic surface here, so it has to go in this direction. But the trouble is, once it gets to this hole, then your question is what happens? Because the Fermi surface just ended. So it goes into the bulk, and it goes into that chiral Landau level over there. No, orbit. No, well, I think that there's flexibility in terms of, so you're thinking about orbits with just parabolic dispersion. This angle is completely flexible because there's a tensor that connects the momentum to the velocity. Yes. Yeah. So I think in this case, this perpendicularness is so that usually you have the velocity and the momenta are parallel, but in this wild system that doesn't really have to be the case. The velocity and momenta can be parallel. Yeah, it goes through the bulk of the material. It goes through this so-called chiral Landau level. Yeah, so the claim is that there are some signatures in the experiment, but I think these are very preliminary and getting worked through. The basic argument is that this part should depend on so there should not be, the claim I think is that there is no, so it's about the thickness and thickness dependence of the period of the oscillation and the amplitude of the oscillation. I don't remember precisely, but if you're interested, so I think Andrew Potter, who was a postdoc with Ashwin and Analytis, are the people who have been writing papers about this. Analytis is an experimentalist, and Potter was a postdoc with Ashwin. Now, this tells you fundamentally that this is not possible. Right? That this is really in fact, the only way the Fermi arc can end is you have this Cairo-Landau level and you have Weil and all of these. No, so if the sample is small, then technically, I mean, if you make it thin enough, then so ultimately this this picture has to be corrected. Yeah, then exactly they'll hybridize with each other and disappear. So there's some finite lifetime. So even the electron here can this arc can hybridize with that arc and sort of go through the bulk if the bulk is very thin. This thing breaks down. Wait, Rajdeep had a question. Oh, I see. No, I think I can tell you some of the things that I've heard of, but I have to say that Majorana's is really what I've been keeping track of more than. I mean, I've been keeping track of these, but not precisely working on it. I mean, so Weil or most of these is the key field that's most active, I would say. Even it's taken over Majorana's, unfortunately. And the issues with, I think one key issue with Weil that is theoretically is tricky is what happens when you have disorder. How much does this survive when you have disorder? Because this relied on the presence of translational invariance, at least naively in its construction. And because it's gapless in the bulk, you cannot make the arguments that you can make with 3D topological insulators about why this is precisely protected. So this is actually I think Pallab Goswami and Sudeep Chakravarti were probably the early people, some of the early people who attacked this question using field theory, their favorite tool. And the answer, naively turns out that disorder is irrelevant at the Weil point because it's just that your density of states is so small that you think that disorder is irrelevant. But then they concluded made a very weird conclusion that the density of states which vanishes at the Weil point, that's the order parameter in this field theory for describing disorder. But density of states as an order parameter, I can already see you squinting at that, is actually very strange because you know that whenever you have disorder, you're going to bring down some states and screw up a zero-dimensional density of states. So, but unfortunately, I think that's the only field theory that's been written down with disorder, with density of states as the order parameter. And it seems, it suggests that there's a transition from a so-called Dirac semi-metal phase to a disordered phase. But then, actually, I think actually this is, I know this because this has been work that's been done at Maryland in collaboration with David Hughes. When you do numerics of the system, and it's actually quite difficult to do numerics because three-dimensional systems are quite big. So you can use this kernel polynomial method, and you actually, ultimately it looks like the density of states actually does go to 0, but not quite to 0. So it's there's what you'd call a weakly avoided quantum criticality at that point. So that I think is, but this is still particularly. What is the field theory? I think what is the field theory description of this avoided criticality, or if there is this question seems very puzzling. So from an experimental point of view, I think this is the usual story with all these topological phases. What are smoking gun signatures for a while? And I guess this is the context in which I kind of got a little bit involved. there was a little bit of, from high energy literature, there was a little bit of a temptation to say that Weil would have a weird signature called the chiral magnetic effect, where if you apply a magnetic field, you would just get a current to flow. The catch was that from the field theory point of view, the regularization of this problem was tricky. It wasn't clear which was the correct regularization. And it seemed that the answer kind of depended on how you regularize the problem. For people like me who really think condensed matter-y, just having a system where you apply a magnetic field is not a superconductor and you get a current sounds wrong. And when I tried to work through this, I learned from the literature that actually you can literally prove this in any lattice system. When you apply a magnetic field, current is zero. You can actually go ahead and actually prove this. So that didn't quite work out. But there are still signatures of this chiral anomaly that people are looking for in experiment. And so whether these hold up and how much these hold up to disorder, and this is one very active area of research. I think another active area is this. So there are some weird things happen when you get near the topological phase transition, or let's say the Bernoulli-Hughes-Zhang model, which was the model for the 3D topological insulator. You get a quadratic touching point at the transition. And when you add interactions to this quadratic, so it's like Weil, but it's not linear, it's quadratic. When you add interactions to this seems like another sort of weird place. And of course, I guess as Vijay mentioned, when you add interactions, what happens to all of this classification? That's another broad avenue. And let me try. So since Majoranas is what I think about most of the time, the story with Majoranas is still sort of in this regime of figuring out, looking at the experimental data and figuring out sort of, it's gone past the pure theory stage at some level, at least for now. And it's a question of collecting more evidence and moving towards a smoking gun signature that, okay, these really are Majoranas. And the progress there has been, there's a Nature paper this year which claims to see exponential splitting of as a function of length. So it's sort of moving in that direction. And then people are trying to see how to do more interesting operations with Majoranas, like look for teleportation or something like that. Anyway, so.
Quick question from Maha.
Oh yes, there was. Yes.
Because that will...
about which degree? Which axis?
Let us say about the kx axis, such that we still have a linearly dispersing mode when I take a section along kx equal to 0 plane. But in the ky equal to 0 plane, such thing doesn't exist. Maybe I can have a parabolic thing in that direction.
Yeah, no, that's a good question. So I don't. Okay, so this is great. This is a great kind of question because this was the question that Andre Bernoulli asked about Weil, and he rotated the Weil cone on its head, and now it's called type 2 Weil. So this is a good way to think and invent things. But I think in this case, it's actually kind of subtle. What I didn't tell you was that the 3D topological insulator in the bulk, it had to have certain specific properties for the so-called magnetoelectric effect. So when you apply a magnetic field, the surface should have half integer Hall conductance. And I don't think this will work with what you're saying. So I kind of went through the quickest route, but it's not the most. So ultimately, if you think deeper, I think it's probably not allowed, but this is true, but I'm worried that but even that fine-tuned point I think has the wrong magnetoelectric effect. So it's important to think about the magnetoelectric effect first. Like whatever you do to the surface, the magnetoelectric there's this E dot B response. The half, which is called the half quantized Hall effect when you apply a magnetic field. This is a topological property that cannot go away even when you have interactions and stuff like that. So whatever you come up with should respect that. That needs to be respected. So I think that, yeah, it's probably not allowed.
Okay, more questions? If not, let's thank Jaydeep once more for the nice set of lectures.
Thanks.